We are now at in-class activity 11C. In 1959, author C. Clarke predicted, I love this quote, 1959, y'all, a personal transceiver so small and compact, 59, y'all, that every man carries one. The time will come when we will be able to call a person anywhere on earth merely by dialing a number. Wow. It did take over 35 years from when the concept of cellular phones emerged in 1947 for the technology to be commercially available in the United States. By 1987, cellular phones, telephone subscribers exceeded 1 million, and the airwaves were crowded. And so remember, just to get your brain going, time, like 1987 would go here, the time, and then over here would be the number of cell phones. And so we're now at 1 million on the time. According to a Pew Research Center study in 2013, over 90% of American adults owned at least one cell phone. So make a quick sketch of a graph that you believe shows the growth of cell phone usage in the United States. It is a great time to pause. And I'll go ahead and redo, like we got time down here, we got the number of phones over here. Because if you do have a choice of time, it is very likely, almost always, going to go on the x-axis. And so you might say at zero time, whatever that is, we had 0 phones. Do you think it's linear? Or do you think it's exponential and going to grow and keep on growing? Or do you think, and it not necessarily is, but do you think it might be where it's got a lot of growth, but then it's got to start leveling out at some carrying capacity at some point? Maybe you think it's a bit of all three of these. Whatever you think, stop, jot yourself a couple of notes here, and then let's unpause, and let's read through the objectives. The objectives say that you will understand the parameters of a logistic model affect its shape. The parameters of a logistic model affect its shape by varying the output. So we're going to look at input over here on time, or various and sundry other variables, parameters. And then what's it going to look like? What does it put out? And then also we'll understand initial population, growth rate, and carrying capacity are the parameters of the logistic model in this activity. And then finally, we should be able to explore the changes and values of the parameters of a logistic growth model and describe the effect these changes make on the models. We got to see what's going on. What does it look like? And be able to put that in words. So the curve that best models the growth of the deer population on Smith Island is also the curve that best models many populations that grow to some limit. This curve is used in biology, chemistry, many other fields. Also, it is useful in statistics. You read in preview 11C that the growth in cell phone subscriptions is slowing down. Well, good to know that it is slowing down. Let's see if I can change pages and it not be slowing down. So in the previous lesson, you worked with a recursive model for which you had to know the previous population in order to predict the next value. But wouldn't it be more convenient to be able to jump ahead several steps into the future without calculating all of the steps in between? You bet. Well, an explicit equation allows you to do just that. You can substitute in any input value and calculate the corresponding output value. And a lot of times, we'll end up graphing it where input is X, output is Y. The explicit form of the logistic model is shown in the spreadsheet image that follows. L, B, and C are parameters for the equation. You will graphically investigate the effect of changing these parameters. Now, I'm not even going to try. I'm going to try to enlarge, and let's see what happens to the drawings and to what we see. Oh, it worked. Okay, I'm going to scroll down a little bit, see if I can enlarge one more time. Ooh, we did it. And so in this little corner piece, you can see that there are several things going on. There is an L, there is a B, and there is a C. Last lesson, you had a piece of paper where you wrote down some vocabulary words, or I mentioned getting some flashcards and putting something on each one of those. Well, L is going to represent our carrying capacity. That line right there. P, well, we'll get to it in just a second. Let's look at C. Well, I don't know if I should tell you all of these things or if I'm going to spoil the surprise. Let me wait and let me go back smaller. I don't want to spoil the discovery here. And let me go on to question number 2. So question number 2 says you will create a graph of the explicit form of the logistic model by plotting points, write the equations shown, and substitute in these values. Go ahead and make sure you've got down L10. I got to make sure I've got it down. There it is. And B -4 and C3, because I'm going to end up, it won't split pages for me. It's going to have to like be one or the other. So here we are at this top one that says now plot the points from your table. And I don't even have a table on this one, and I must have missed it at the bottom of the other page. Nope, it's right there. See if I can get it all on here, and there it is. Oh, one more. And so we have T and we have P. And so let's say T is time, and let's say P is population or maybe number of cell phones. And then we had a formula on the other page, P equals, and they asked us to plug stuff in. They asked us to plug in the carrying capacity. They didn't say that, so I'll just say they said plug in the C and plug in the B. And now they're asking us for each one of our values of T, plug it in and get a number. Plug it in, get a number. Plug it in and get a number. So I want to walk us through one of these, and then I'm going to pause, do all the rest of them, and then come back. So they are asking us to plug in, well, that's a real nice one. Why not do it? So let's start with this one. They're asking us to plug in that value in place of T. So I'm going to go grab my calculator, because now this right side has all numbers, and we can punch them in and we can get a number for P. So how you punch this in is going to be totally up to you. I'm going to do this one using a whole lot of parentheses. I'm going to go forwards. A lot of times I go backwards, so I'll go forward on this one. I'll end up punching in 10, and then I'm going to punch divide by, but I gotta tell that calculator what I'm doing. This parenthesis says, hey, I am in the denominator. 1 plus parenthesis, oops, working on a fraction to the -4. And then I got to finish it off and say like, hey, dumb calculator, this is what we're doing. And I'll probably still need to hit equals, but that's the process I want to do on this one. So I've got my calculator, and I'm going to type in 10 divided by, open a parentheses, 1 plus, open another parentheses, 1 divided by 3, close that parentheses, send it up to 4 negative. I have to do -4. And close the parentheses, hit equals, and the number that I get about is 0.12195.122. They don't tell us where to round, but if I look in the chart, they were already rounding to the 100 dots. And so this is my hundredths place. I look behind it, and it says don't do anything. So I get 12 hundredths. So I'm now going to pause the recording, go work on the rest of these, and then come back. I suggest you do the same, and then come back and let's compare answers. So I have my table filled in. You might want to freeze the screen and double check what you've got, because it says now plot these points from your table on the following plane and connect the points with a smooth curve to create a graph. So here we go. It's always really good to have a zero, and zero would be the time. And so I will wait. That's so hard not to do. I'm going to leave it alone because they didn't tell us to do it on this one. I will just follow what they have for us. So it says starting at when you have a half. So a half is going to be here. Then we'll end up doing 1, 2, 3, 4, 5, 6, 7, 3, 4, 5, 6, 7. So at a half, we're at 0.01. So man, that's just like a penny down here between a dollar, I'm sorry, $0 and $2. At 1, we're at a 12th. Sorry, 1200, which is just a little bit better. 2, we're at 1.65. 3, we are at 5. 4, we're at almost 8. And 5, we're at almost 9. 6, we're over 9. And at 7, well, we're a little bit higher, just a little bit closer. And y'all look at what's happening. We got us a nice little kind of logistic curve that looks like it might have a carrying capacity. Pause as you need to. I'm going to need to go ahead and pause because it says for the next part, let's open up a spreadsheet and take a moment to familiarize yourself with the graph and the sliders. And then we're going to play around with that, looking at all the pieces and the parts of what we've got. So having said that, I will stop at this. I think I've already got it pulled up, so I can do a new share. Yep, and go to the Excel spreadsheet, and you should be able to see what I've got on my screen. And I want it to be larger, but I don't want it to be so large. Let me see, got it this way. Okay, maybe that, no. Maybe this, let's try it at this. No, because it's still not even showing me the formula. Now it does. Okay, so it's asking me on number 3, part A, on the plane in question 2, put and label the horizontal line at P is 200. Oh, there it is. Let me see if it's going to let me draw. It may or may not. Let's try. Come on, hang on, one more try. No, it's not let me. Oh, there it goes. Oh, yeah. It's saying notice this right here, and we need to set L at 200, and there's our L, our carrying capacity, our limit. And then it says, let's let this B, which we haven't talked about what it is, but it's going to be a growth rate. And then C, well, let's see if we can discover what C is. So they want B to be -4 and C to be 25. Here we are. And so it says to label this at 200, and we're going to call it an asymptote because that means you get darn close to it, but you don't touch it. And it does happen to represent that we have a carrying capacity of 200. And notice that this curve approaches it, but doesn't seem, this blue curve approaches it, but doesn't seem to touch it. So now use the slider to change the value of L. And while we're doing that, it says, watch the changes to the curve and how does the value of L affect the shape of the curve? Write your conclusions in complete sentences. For example, one sentence might begin with the phrase, as the value of L decreases. Okay, so here's L. Let me not be drawing. So let's play with L as L decreases. So I want you to watch the curve. And what do you notice the curve is doing as L decreases? And you figure out what words you want to use, like getting squished, shorter, shrinking, going down vertically. But also notice that dot in the middle. Is the dot staying the same? Is it moving around, or is everything just getting squished? Another sentence might start with the phrase, as L increases. What is happening? And you can talk about that carrying capacity. There's the 200. But then as the carrying capacity stretches or goes up, it looks like the curve stretches. As it goes down, it looks like the curve shrinks. What are you going to say that's going to make sense to you and click for you? A comment could be, as the value of L decreases from the 200, the carrying capacity decreases. And as the value of L increases from 200, the carrying capacity increases. So the value of L determines the carrying capacity of the population and is the, I got to tell it, let me write. What was I just saying? Maximum. That this carrying capacity is the maximum value of our curve. Okay, well, that's pretty cool. Let's go into part C. Put the value of L back to 200. I'm there. Now use the slider that controls the value of B, and watch the curve as you do so. And how does B affect the shape of the curve? And B is what we're going to call a growth rate, the rate of the growth. And so let me start going negatively first, so going down first. So going down, what do you notice about the curve? Ooh, whoa, that's weird. Do y'all notice how it's kind of twisting? Let me go back up. That's kind of real spiked. Like this curve, well, I can't, yeah, it's like real spiked straight up. Sorry about those weird dots. Now, when I start going down, well, I'm so sorry, I'm saying it wrong. We're getting further into the negatives. And as we get further into the negatives, going down, this middle part gets more steep. But as I get going the other way and get closer to zero, as I'm getting closer to zero, it's flat. Oh my gosh. It's flattening. Oh, and then when I start going back down, it starts pulling back into that S shape. So however you'd like to write it, whatever that means for you, let me get it back to 4. Whoopsie do. Up, 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 up. There we go. Whatever you'd like to write. It could be something like that. As the value of B decreases from -4, the curve rises more sharply. The rate of increase initially, sorry for the yawning, excuse me, making this one pretty late at night. This over here, it is the rate of the increase initially is much greater. I mean, it's got a good little spike going on right here. But as the value of B increases from -4 and going up to that 0, what am I trying to say? The curve, it doesn't rise as fast back here. It's more flat. It rises more slowly. The rate of increase initially is slower, or is lower, and it's slower. And the value of B determines the rate of increase, the growth rate, the rate of increase for the population. So then part D says, let's put this one back on -4, and then use the slider that controls the value of C, watching the curve as you do. How does the value of C affect the shape of the curve? So here we go. We're at 25. Let's go down from 25 off on the writing. And let's see what it does going down from 25. Uh-oh, our dot's moving. Our dot is finally moving. Oh, I lost it. Let me go back the other way. The dot is not going up and down. The dot is just sliding across 100. Sliding across the 100. So what do you notice? We were on 25, right? Yeah. We were on 25. And so as the value increases from 25, it takes longer for the curve to begin to rise exponentially. It gets a little flatter. And then the inflection point has a larger T value because it's going, I need to be drawing. It's going this way, so its T increases. And then as it decreases from the 25, I'm just drawing over the little 25 there, as it decreases from the 25, then our, what am I trying to say? The curve, am I writing? Yes, the curve gets a little bit taller, faster, spikier. It must begin to rise more quickly. And this inflection point has a lower value. It's going that way. So part C, what significant change in the shape of the curve seems to happen at the large point in green? In other words, how are the two portions of the curve to the left of the point and to the right of the point different? So I'm going to clear my drawings. We are now back at where we were supposed to be with the 25, -4, and 200. And so if you haven't been pausing, pause, write a thought about part E, and then come back. But something we could say about part E and this green dot is that the large point is our inflection point, and it's the place in the curve where it changes from increasing at an increasing rate to increasing at a decreasing rate. And so part 4 says, as you investigate each of the 3 parameters, describe what happened to the large green point. Well, the point is representing the inflection point, and it is always, 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 always between the 2 asymptotes. And so it is always, if this is the carrying capacity, the L, is an asymptotic line. And then down here at 0, we have an asymptotic line because it's backing up to it, but should not be touching it. Then this should be halfway in between. I'm at 0 and 200 for my asymptotes, and 100 is in between. And so if I let my carrying capacity, quit making dots on the screen. If my carrying capacity goes down, my inflection point has to go down to keep up with it. Like now, I'm sitting at trying to change colors, never mind. I'm not drawing, so it's not going to let me. Now I'm down to 100. I'm between 0 and 100. So what's halfway? You guessed it, 75. And so as the curve rises more slowly, then that point is going to move to the right. So it's going to move around, and also going to stay halfway between the 2 asymptotes. So let's finish up this lesson. It is talking about part number 4. So let me go ahead and change screens and get back to, let's do a new share, get back to our words. And scrolling down, I've done several pieces. I'm trying to get down to part 4. And it says the number of deer in a fixed space, like an island, will likely have an upper limit. A logistic model is appropriate because the population will grow slowly as it reaches that upper limit, which is the carrying capacity. Question 1 asked you to sketch the graph that you think represents cell phone usage in the United States. And you might have chosen your graph to show the number of cell phone users or the percentage of the population that are cell phone users. But part A, suppose you choose a graph to graph the percentage that are the cell phone users in the United States, and explain why a logistic model would make sense for your graph. So just a couple more parts in this lesson to pause and to think on. But something you might want to write down is the percentage of the population that owns cell phones has an upper limit of 100%. Since most people today in cell phones own cell phones, then the percentage is very likely to 100%. But then you got to talk about who all are you talking about? Like everybody, newborns, 3-year-olds, 7-year-olds, who is everybody? I'm not seeing that it says adults, and maybe I missed that earlier. But then part B is suppose you choose to graph the number of cell phone users in the United States. In what ways is the logistic model not a perfect model to describe the number of cell phones in the United States? Well, For one, the United States population is changing in size, so there's not a real clear upper limit to the number of cell phone users. And also, if you haven't already thought of this, we're not bound to only having one phone. So some people, like my husband, he has a work phone and he has a personal phone. So he's got two on him all the time. So even if we maxed out the population, we would continue to increase the number of phones. Thus, the upper limit for the number of cell phones in the United States really can increase. So on that note, we are done with lesson 11. Let me double check the letter. 11C. Make sure you go do the appropriate practice for 11C.